Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us begin solving this step by step. Reaction A. Cyclohexane carboxaldehyde to 1-bromo-1-formylcyclohexane. The starting material is cyclohexane carboxaldehyde. The product has Br at the alpha carbon, C1 of the ring, which is also the carbon bearing the ChO group. This is alpha bromination of an aldehyde. Alpha bromination of carbonyl compounds is carried out under acidic conditions using Br to H+. Under acidic conditions, the enol tautomer forms and reacts with Br2 to give the alpha-bromoaldehyde. Br2CCl4 is a radical or electrophilic addition reagent, not selective for alpha position of carbonyls, and Br2HO gives polyhalogenation, haloform reaction tendency, so Br2H+ is the correct reagent for mono-alpha bromination. Moving on to the next step. Reaction B. 1-bromo-1-formylcyclohexane to cyclohex 2-Na-1-carbaldehyde. The product has a double bond introduced in the ring between C2 and C3, i.e., adjacent to the carbon-bearing ChO, and the Br at C1 is eliminated. This is a dehydrohalogenation, elimination of HBr to introduce a double bond. For elimination reactions, alcoholic KOH, ALC. KOH favors E2 elimination, Zaitsev or specific regioselectivity, giving the alkene, whereas aqueous KOH favors substitution, SN2. Since we need to form the alkene, C is equal to C in the ring, ALC. KOH is required. And for the final step, option A. Br2CCl4 does not selectively brominate the alpha carbon of an aldehyde. Incorrect for step A. Option B. Br2H+ is correct for step A, but KOH for step B would favor substitution, not elimination. Incorrect. Option C. Br2H+ correct for step A, ALC. KOH correct for step B. Both steps match. Option D. Br2HO tends to cause multiple halogenations, haloform-like conditions. Incorrect for step A. Therefore, the correct answer is C. Therefore, the correct answer is option C.